Hello, everyone. Welcome to the session for Eurographics.
Welcome to the session for Eurographics.
Okay, I should really know better. So once again, welcome everyone for the Eurographics full paper session 14, Spatial Queries. I'm jumping in as one of the emergency chairs, as we couldn't get a hold of the original chair. So I hope that this is going to be a very interesting session. So the first talk that we're going to listen to is going to be presented by Floyd Chitalou, and it's going to be on binary ostensibility implicit trees for fast collision detection. So let's go with that.
This is a talk about our paper, which is titled Binary Ostensibly Implicit Trees for Fast Collision Detection. Collision detection is a fundamental and important ingredient in computer graphics, especially in areas like physics-based animations. In the specific case of parallel collision detection, the goal is simply to reduce the time to find contacts. Data structures are also an essential part of collision detection for culling the search space of potential contacts. And when combined with GPU parallelism, further performance can be achieved, which is the focus of our talk today. Thus, the overall objective is to quickly find a set of potential colliding pairs using parallelism, and while doing so, it is essential to be able to update the underlying acceleration structures fast enough in order to detect and handle collisions in reasonable time. Now, several challenges do exist in parallelizing collision detection on GPUs. First, building acceleration structures like the bounding volume hierarchy in real time is a challenge. This is because sorting polygons as well as constructing and updating tree structures can often prove slow for frequent updates. Second, the separate but closely related task of evaluating one or more bounding volume hierarchies for overlap is equally, if not more, expensive. This is because workloads from evaluating the bounding volume test tree can scale from tens of thousands to millions of intersection tests. Therefore, a common approach is to build the BVH once and then refit, combined with the notion of front tracking. The notion of refitting here refers to situations where the BVH itself is built once, and then the individual bounding volumes are resized according to mesh deformations. Notably, this can degrade BVH quality, especially when severe mesh deformations occur, since the hierarchy structure remains constant. Regarding front tracking, it is about caching the bounding volume test tree nodes where the traversal operation stops, and then reusing them for the next time. While beneficial in some cases, front tracking has the potential to negatively affect performance because we then have to concern ourselves with additional memory management and synchronization. Also, the memory cost of storing the cached bounding volume test tree is also another issue, especially when treating self-collisions with high-resolution meshes. Thus, refitting and front tracking seem not quite enough for parallel collision detection on GPUs. For a moment, let us look at how others have tackled this problem. Existing parallel collision detection methods using the bounding volume hierarchy are heavily dependent on front tracking. Some authors like Tang et al. Have proposed modifications to this approach, but with only incremental effect. Furthermore, GPU parallelism can only be exploited with a sufficiently large front, which has the side effect of higher memory costs. More recently, Wang et al. Presented the fastest BVH-based method. They proposed to reorder and restructure the collision fronts in memory, thereby reducing irregular memory access patterns on the GPU. Unfortunately, however, the benefits of their restructuring scheme are offset by the cost in scenes with large deformation. They then must fall back to BVH refitting and front tracking, which is not always what we want. Then the next question is, how about we just try to rebuild the BVHs from scratch at every frame? Well, in this context, Morton codes have proved to be an effective approach to sort mesh polygons on the GPU. These polygons represent the Morton curve, which is also called the Z-curve. And in practice, the triangles of our meshes are assigned to the Morton codes and then sorted in order to capture their relative order in space. From them, we've seen a couple of construction methods. And the fastest construction techniques calculate the BVH structure from the Morton codes themselves by analyzing node split positions and calculating the indices. This analysis of node split positions will affect performance and can serve to constrain rebuilding the BVHs on a frequent basis, just like we desire. Thus, I'm going to argue now that GPU-based collision detection methods are limited in their BVH representation. In particular, traversal is directly linked to BVH structure and quality, which enforces a dependency on refitting and front tracking. So we want to break the BVH construction performance barrier to permit frequent BVH rebuilds. Now for the rest of this talk, I'm going to have three parts. First, I'm going to introduce and describe binary ostensibly implicit trees and explain why they are useful for collision detection. Then, I'm going to present how this new data structure allows for even faster BVH construction compared to previous methods. Finally, I'll present some results for BVH construction and collision detection performance. So let me describe a little bit more about binary ostensibly implicit trees. What we are going to do is take this little mesh object with a bounding box for each triangle, such that we can calculate the Morton codes and then sort them. And we basically want to ask ourselves, what is the implicit hierarchy representation given just the order of the Morton codes? And so, we can assume for now that the triangles of our mesh are sorted. Then, all of our efforts focus on these triangles, and I'm going to introduce the following tree to represent our hierarchy. This layout is of course just an implicit binary tree, which supports analytical indexing. But now here's the key part. We're going to encode this tree according to this shading that you see here, in order to sum up all the nodes in the green area. I've grouped the two types of nodes together as real and virtual nodes. The real nodes correspond to some data that we will actually store about the tree, but the virtual nodes are not materialized in memory. Thus, rather than deducing the topology from the Morton bits, as in previous methods, our motivation is to use the implicit tree for final topology. And most importantly, we will encode this logical implicit tree in a novel way to avoid the excessive storage costs due to padding. I will now explain on how we encode this tree layout without any padding or pointers in memory. Our encoding is based on calculating the total number of real nodes given the number of triangles. Thus, our first problem will be to find the number of real nodes, which I will show you with this example. Given a perfect implicit binary tree structure, we assume that the nodes are associated with a number, and this number is called the implicit index. The size and how many levels of this implicit tree is determined by the number of triangles from our mesh. And from the number of triangles, we will create an array that contains only the real nodes, which is our goal. This leaves out the virtual nodes as merely placeholders. So for this particular example, I have 11 triangles, resulting in 8 virtual nodes, and I wish to find the number of real nodes. So if we forget the labeling for a moment, we can see our problem a little bit more clearly. Thus, we just want to define a function which, given the number of triangles, returns the total number of real nodes. Note, however, that defining this function requires us to figure out how to calculate the number of virtual nodes. So let us see how we can do that. We calculate the number of virtual nodes as follows. Given the number of virtual leaves, we find the largest powers of 2 that sum up to this number. Each power then represents the leaf nodes of a virtual binary tree. In this case, we have just 2 virtual binary trees. We can then find the real nodes using the total sum of virtual binary tree nodes. And interestingly enough, the sum of all virtual binary tree nodes can be calculated using simple bit counting and integer arithmetic, which is extremely fast. Our paper does contain a little bit more detail about this, but briefly, however, our solution comes from the binary representation of the number of virtual leaves. This number uniquely encodes the powers of 2 that we need to calculate the virtual nodes themselves. And so, given our initial problem, if we can find the number of virtual nodes, then we can also get the number of real nodes. Furthermore, just like for the virtual nodes, we can also use some nice bit twiddling to get the number of real nodes, which is also very fast to compute. So far, I have described to you how we can calculate the number of real nodes in our tree from the number of triangles. But one question remains to be answered, which is what is the memory index of a real node given its implicit index? Answering this question provides us with the final piece to our puzzle, allowing us to efficiently translate indices in the virtual padded tree to addresses in memory where the padding itself is omitted. So then, to calculate the memory index, recall that we have a binary tree with nodes labeled according to this scheme. And for each level, we have real nodes occupying the leftmost slots as the virtual nodes reside on the right-hand side. Thus, if we, for example, take any node on the last level, we can easily calculate the memory index of this node by simply counting the number of elevated virtual nodes above this node. And this is in effect the essence of how we calculate the memory location of a real node, and more details can be found in the paper. The concept is in fact similar to counting the total number of real nodes given the number of triangles, but this time we care only about the elevated virtual nodes. Here I show a more concrete example of what is happening. Thus, we can see that a real node is mapped to a memory location at an offset, and where this offset itself is dependent on the virtual nodes above that node. I have shown you 3 segments here, and we can see that in the first segment we have a one-to-one mapping between indices and the virtual padded tree indices in the virtual padded tree to addresses in memory. As we move to the second segment, the memory address offset is trailing by 1, and then it trails by 3, and so on. This overall describes the encoding of our binary ostensibly implicit tree. Now, having described the overall idea behind our tree layout, I will now describe how we build a BVH using this representation. We target a GPU implementation, so that will be the focus of this part. To recap for a moment, I have already previously mentioned the BVH construction algorithms shown here, which are the fastest methods on the GPU. The first method by Karas gave us a fast reduction algorithm to generate the tree from sorted molten codes. This method, however, required 2 GPU kernels to build the tree, which limited performance. Apertree extended this method in 2014, requiring just 1 GPU kernel and with faster performance. Finally, I also point out this method by Klein et al., which is the lightweight BVH, and it is similar to our method in the sense that nodes can be indexed implicitly. However, our method is more efficient and better suited to the GPU parallel setting. Thus, in broad terms, our approach shares some aspects with these techniques. First of all, we have an implicit structure like Klein et al., but with a novel encoding. Second, our tree construction uses a parallel reduction like Karas and Epitree, but without need to track radix key ranges. I will now describe a little bit more about how we build the BVH using the binary ostensibly implicit tree. An overall construction pipeline looks like what we have here, whereby we build molten codes from mesh triangles, which we then use to construct a bounding tree structure. For this section of the talk, I'm going to focus just strictly on this part here. I will describe the basic idea of our approach, which is to utilize Morton order and a specific node layout, which is implicit in our case, to establish a mapping between GPU threads and BVH nodes. For a given number of triangles, we can infer what the final implicit tree structure will look like. This means we can ignore the non-existent parts. From the implicit layout, we then map GPU threads to the remaining real nodes on the starting level. In some instances, it may be necessary to pad threads for scheduling purposes. Then, given the number of threads, we can then organize these threads into groups. Each group then maps to a small subtree of real nodes to be processed, which is also beneficial for performance. All groups then process their independent subtrees separately from one another until the subtree root node is reached. The subtree root node is a point of synchronization, which unifies global communication and also memory accesses as well. This process is repeated over multiple iterations in order to build the full tree, which you can also see here. And what is nice about this approach is that threads are always guaranteed to be able to utilize local shared memory, which is fast. And if we wish, we could also build the tree in one kernel. Our paper contains more details about this. So then, let us look at the results now. To evaluate our method, we implemented a software prototype using just standard C++ and with OpenCL, which was run on the GTX 1080 GPU. We evaluated our method both for BVH construction and also collision detection as well. For BVH construction, we used standard 30-bit Morton codes. We evaluated performance by comparing with the LBVH and focusing strictly on the time to build the hierarchy and bounding volumes. We have used 5 publicly available measures to evaluate this performance, and our results for BVH construction are significant, where we achieve over 6 times better performance as compared to the state of the art. And even in the worst case, we also see strong speed up, which is over 4 times faster. Here we compare based on the number of BVH nodes. This time, we also include the full perfect implicit tree with which padding is required. From this table, we can see first of all that our tree requires significantly less memory than the fully padded tree. And when compared to the linear BVH, we use approximately the same number of nodes, which is near enough the optimal size. Thus, we maintain the benefit of implicit trees without restrictions of padding, making our method both fast and also memory efficient. We also evaluated BVH quality based on the surface area heuristic and compared against the linear BVH. As a categorically fast construction approach, our technique emphasizes build performance and simplicity, which can limit BVH quality in some cases. The quality of our tree can degrade by over 2 times compared to LBVH, and this is because we simply pair nodes at each level and without looking at the actual radix bit values to construct the hierarchy, unlike the LBVH. And further details about this can be found in our paper. To evaluate collision detection performance, we also integrated our new BVH tree into a custom pipeline and compared with the restructured fronts approach by Wang et al. Our BVHs are rebuilt from scratch at every frame in order to demonstrate the efficacy of our tree structure. In addition, all comparisons in this case include BVH traversal and narrow phase collision detection, which calculates triangle intersections. And for this task, we used 4 publicly available benchmarks, and our results are as follows. Our pipeline is up to 29% faster on the evaluated datasets, and in addition, memory usage is considerably less, making our method faster and also more memory efficient. At best, the state-of-the-art BVH-based techniques build the BVH once, and then simply refit bounding volume extents at every frame. This has the effect of degrading overall efficiency. With our approach, however, not only is it feasible to rebuild the BVH at every frame, but our technique can be faster than refitting. In summary, we presented the binary ostensibly implicit tree, which is a logical layout for storing implicit trees without padding. It does this by making it possible to efficiently translate indices in the virtual padded tree to addresses in memory where the padding is omitted. With this new structure, we were able to achieve good performance with BVH construction. Consequently, we were able to perform collision detection in a reasonably short time, and with BVH construction occurring every frame. And finally, although our experiment showed some good results, some points remain for consideration. In particular, one disadvantage of implicit trees is that they're not easy to modify once constructed, unlike explicit trees. Thus, opportunities for improving quality can be limited, but we consider this a trade-off. Thanks very much for your attention.
Great, thank you very much for this very interesting talk, and we're just waiting for some of the questions to come in via the YouTube and the Discord. So I guess I can start with a question that might seem very dumb because I'm not very that familiar with the topic. So in your implementation, you mentioned that you're assigning the GPU threads to the bottom layer of your LOD tree first, and then you basically traverse up. So have you investigated how it actually works if you have like a very deep tree? Because then you all of a sudden get a linear, like not linear, but a logarithmic like performance of your application.
How deep is deep in this case? Because in our scenario, we just assume that you could have, say, 1 million triangles and you'd still build the tree that way. So
okay.
Yeah.
No, I was just wondering in general, like on which size of data sets have you tried it? You showed a few of them in your presentation, but just like going through the paper, there were a couple of more. Like, what's the largest data set or like model that you've used?
I see. We tested, I think that was about 2 million triangles. Yeah, 2 million.
And you would assume that if you like scale it up to, let's say, 200 million, then you would basically get a pretty much logarithmic increase, or?
I would expect something like that, at least to the point that it's really the hardware that just dictates the performance at that point. Yeah.
Sure. Have you also thought of, like, I'm not sure if that's what you do with the implementation, but are you fully finishing with one of the layers of the tree before going to the next one, or have you thought about doing some more dynamic scheduling there, that if you know that you have one subtree already finished, you can go to the next, or something like that?
So it's within an individual subtree, it's asynchronous, but the moment that we should reach the root level of the subtrees, there's synchronization there. So we actually have two implementations. One of them enforces the synchronization each time you reach the subtree root nodes. But in another type of implementation, which is similar to Keras, we can actually still continue the execution once you reach the subtree root nodes. But when you reach that point, you actually have to start relying on global atomic operations. Yeah. So the benefit of working within the subtrees is, of course, that you can rely on just local atomic operations, and then also using local memory to cache your operations, which is extremely fast.
Yeah, that makes sense. So we got one question coming in from Andreas Vasilakis. Have you tested against optics tree-led reordering BVH, the TR-BVH, and what version of optics have you used for the performance evaluation?
We have not evaluated against any optics implementation, so I cannot provide any further information there. So we only compared against the linear BVH by Apertree. Yeah.
Would that be something that would be interesting to do for the future work, or do you suspect anything surprising coming out of that, or?
I would rather not say anything without actually measuring something. So I think it's it's certainly something worth trying out. And we've also perhaps thought about trying out other layouts of the tree itself, like using the depth first search layout, or the other layouts like the Van and de Bois layout as well. Yeah.
Yeah, that sounds great. All right, I think there are no other questions coming in, so I think we can jump over to the next talk, which will be real-time anticipation of occlusions for automated camera control in toric space, which will be provided to us by Ludovic Burke.
Cameras are a really important feature in most of interactive applications because we often want to follow targets. For example, in simulation, CIO, or cultural restitution applications, we want to follow decor or interactive elements. In third-person video games, the camera follows the character we control by framing it in the center of the screen. And sometimes, we also want to track another character or an object we interact with. The main problem of these applications is that the camera is not trivial to control for casual users, and that's why we want to automate camera system. Our objective is to design one, but for real-time applications and for fully dynamic environments. But what makes a good automatic camera system? First, it have to be able to frame the targets. Indeed, as we want to follow targets, we often have constraints on where they are displayed on screen. The targets are what we want to see on screen. That means the system have to make sure it continuously maintains visibility on them. Finally, for the experience to be pleasant for the user, the camera trajectory have to be smooth. How can we build such a system? Let's address each problematic at a time. The first problematic we have is the framing. To satisfy this constraint, we use the toric space. The toric space is a space made for a camera to frame two targets. For a given on-screen position of each target, the toric space gives us a continuous space of camera location satisfying this exact constraint onto a torus around the two targets. This is perfect for us, as we rarely need to frame more than 2 targets. But we still need to address the visibility problem. In the literature, a lot of works address partially this problematic, but without the framing constraint. For example, this paper of Oskam addressed the occlusion problem for a dynamic camera, but this system does not work for dynamic scenes and need heavy precomputations. And indeed, visibility is complex and expensive to compute. Commonly, in real-time application, the visibility and collision of the camera are checked by simply casting rays between the camera and the target. Indeed, rays are low cost if used consciously, but this is exactly the problem. If we want to fully automate the camera control, then recasting becomes too expensive. Why? Let's develop a use case of how to move a camera avoiding occlusion by testing visibility with raycast. In order to evaluate visibility, we launch rays from the camera towards samples picked on the target surface. And the average number of rays that actually touch the target define the visibility. But obviously, the more rays we launch, the better the precision. That means the complexity of our visibility estimation is the number of rays we launch. And if we need to see more targets, we also need to multiply the number of rays by the number of targets. And this provides an evaluation at time t. But the scene is dynamic, so to know their future visibility, we again need to multiply by the number of frames we anticipate on. And this for a single camera configuration. If now we want to move the camera, then for the next frame, we need to know where to place the camera. This is why we need to do the same for other many camera locations. So once again, we need to multiply by the number of camera locations we sample. So we clearly see that for cameras, raycasting can become very expensive and provide very discrete informations. If we take the problem upside down, we can test if the camera is occluded from the target point of view. We can even test the depth instead of testing if the ray reached the camera or not. And the depth problem is something well known in rendering with the depth map. Thus, instead of using raycast, we'll use rendering to evaluate visibility by computing shadow maps. To address our 3 constraints on the camera, what we propose is a computation pipeline which mainly relies on toric space and maps. First, to satisfy the framing constraint, we propose to use the toric surface, onto which the camera will remain. Second, to find non-occluded locations on this surface, we propose to compute dedicated shadow maps. And because the scene is dynamic, to anticipate future occlusions, we propose to go further and generate anticipation map. Finally, to create smooth camera motions, we propose to search in the anticipation map while following a physical camera model. Okay, let's start with the projection on the toric surface. To well understand how we proceed, considering the camera at the toric coordinates theta phi, we use 2 representations of the toric space. The first one is the original toric representation, where the camera position is given in the world space. The second representation is the 2D representation. We use it for the maps of the toric space. The camera position is given in the texture coordinates. Knowing this, we compute 2 maps per sample picked on the target surface, by projecting information on the toric surface using shadow mapping principle. The first map is the visibility informations, and to be able to anticipate the future occlusions, we also need the velocity information of the occluders that we compute on the velocity map. The visibility map is computed by comparing the toric depth and the occluder's depth. We fill the map at the texture coordinates reached by the projection prism. In this sequence, you can see on the toric surface 3 colors. The green color is the non-occluded area. The red color is the occluded area. And the white color is where we don't have any visibility information. In the same way, we compute the velocity of the occluders relative to the toric surface tangent basis. By derivating the position of the toric and the occluders, we have their velocity, and we transform the relative velocity in the tangent toric surface basis. This gives us the 2 map, as the image shows here. We use this map to compute the anticipation map. To illustrate how we compute the anticipation map, let's take an example. Here, the black circle represents the projected occluders on the toric surface. If we take any pixel of these occluders on the shadow map, we can have its corresponding velocity on the velocity map. Considering that the occluders follow a physically plausible trajectory, we can define an area that defines the most probable place for the pixel to be the next frame, taking into account both linear and angular speed. The further we are from the center of the area, the less likely it is for the pixel to be, and whenever we are out of the area, the probability falls to 0. Let's take a look at how to compute the probability of a pixel at the position theta phi to be at the position theta prime phi prime, the next frame. Knowing that we define this area using linear and angular speed, we define the uncertainty the same way. Considering the two vectors v1 and v2, we define the uncertainty function u that compare the two features. We apply a decreasing linear function between 0 and 1 on the norm difference and the angle between the two vectors. Now that we know how to anticipate using the two maps, to have the anticipation map, we integrate the shadow map along the velocity using the uncertainty function. This anticipation map is from one sample. To obtain the final anticipation map, we do the mean of the anticipation map from each sample. With this prediction of the future occlusions, we can now start moving the camera. But remember, we not only need non-occluded camera positions, but we also need a smooth camera motion. So to choose our next position, we use a set of strategies to sample future camera locations in the anticipation map. In the first two strategies, we consider the camera as a particle that have a position and a velocity following a physical model. The same way as previously, we define an area defining the freedom of the camera depending on its velocity and its position pi. By minimizing the anticipation on the research area, we find the next position of the camera p hat on the map. After moving the camera to its new position, we update its velocity vector by derivating the camera position and multiplying it by a damping force. To avoid the camera to tremble, we consider that the more a camera is fast, the less open its freedom angle is. And in order to let the camera move at low speed, we define an initial push for the camera to move when occluded. It would be simple to move the camera in the map basis, but the toric space have a lot of distortions. That's why we define the camera velocity in the wall basis and search in the tangent plane of the toric surface. Then we project the solution on the toric surface. If there is no solution found by the physical model, we define the look-ahead strategy. We basically extend the research area to check if there is a better solution further. If we find one, we move toward it but staying in the single frame strategy area. If again no solution has been found, we consider that the camera is in a local minimum and we relocate it at another position on the toric space. The problem here is that, as the image shows, we have the visibility information only inside of the projection prism. That's why, in order to sample the visibility, we rely on recast without anticipation. It's okay, because our goal here is just to let the camera escape the local minimum. And, as there is no anticipation, we don't launch many rays. To present our results, we've made 3 different benchmark scenes, demonstrating different aspects of the system. And a challenging scene that's closer to a real scene, made with a lot of sparse occluders. In each presented video, there is an anticipation map state, with the camera position. The map is displayed in the right lower corner of the screen. The first scene is a corridor with turn. The first target is the character that's walking. The second target is a sphere that represents the character's line of sight. In this sequence, we can already observe the benefits of the anticipation when the character turns. The camera anticipates and moves in order to always see the 2 targets. In comparison, if we remove the anticipation, we can clearly see that the camera waits to be occluded before moving away from the occluders. We also tried to evaluate visibility with raycast, but without anticipation, because it would be too expensive. And as expected, the results are close to the version without anticipation. In this second scene, the goal of the camera is to find a way, being in the other side of the wall, to see the character that is the only target here. At this moment, because the anticipation is a gradient and the look-ahead strategy, the camera managed to get out of this occluded area, while it can't without the anticipation. And here is the full sequence without anticipation. The camera movements are less smooth, and there is more occlusions. Unlike the first scene, we've run this one with the evaluation of the visibility with raycast. And the conclusion is the same. The results are really similar as the results we have without the anticipation. As we have not seen any cut yet, let's enable it here. As you can see, the camera goes in front of the character in the corridor. And this is not the purpose of this scene. So, we also propose to combine our anticipation map with a custom map, handcrafted, which we call style mask. They are for the designers to specify a preferred viewpoint, or, in other words, where the camera can go on the toric surface. Here, as a demonstration, we designed a mask that forces the camera to remain outside of the corridor, thus providing more interesting cuts. In the third scene, we have two characters walking side by side. The targets of the system are their upper body. A part of these result videos, we have also made a set of numerical benchmarks, which I will present while the videos are running. First, we wanted to know the influence of the map size on the performances. We've tried 4 different map sizes, from 64 by 64 to 512 by 512. As you can see here, with a 64 by 64 map resolution, we are close to 200 FPS, while the map size do not impact the visibility significantly. We have also compared the visibility average on 3 other benchmarks. We can see on this graph that the average visibility score is better for our system. On this graph, R is for the raycast visibility estimation technique, and W is for our technique without anticipation. For the same 3 benchmark scenes, we have also compared the camera motion features with the speed and the acceleration. What we can see here is that for our system, we have in average higher speed and higher acceleration than the 2 other techniques, without anticipation and with raycasts. And indeed, we always have a compromise to make between visibility and camera smoothness. This last scene is more challenging. The two targets are the upper body of the character and the red sphere that represent the character line of sight. The sequence is divided in 3 sections. In this first section, there is a lot of sparse occluders, and the camera managed to avoid them all. In this second section, there is dynamic occluders. The system anticipates their displacements and manage to maximize the visibility on the targets. The final section is a mix with sparse and hard occluders. So this paper introduces a real-time virtual camera system that works for fully dynamic scenes, that is able to frame the targets using the toric space representation, maintain the visibility on 2 targets, and ensure a smooth camera path using physical camera displacement model. For our future works, we have different approaches. First, as we only use the toric space for now, we could make the system more generic and use other surfaces. Second, for now, the system is constrained on the 2D surface. We would like to extend the system to a fully 3D camera motion model. Also, we'd like to account for directorial styles and specify to the camera what kind of shots it can do. Finally, now that raycasting is hardware available and more accessible, with the new RTX technologies, it could change our perspective on raycast. Thank you for listening.
All right, thank you for that presentation. So we can start with one of the questions that we got from the YouTube right away from Kevin Allain, who first of all says it's great work, and I would agree with that. And he's asking, you kind of hinted to that, but still it might be good to rephrase that, restate that, is how does your system adapt to distance restrictions, for example, being forced to be far from the objects of interest?
Actually, this is tricky because the further we are from the targets, the less precise we are with the map size. So you have to have more resolution on the map size. So it will be a little bit more expensive to compute. So, yeah.
Is that something that would be possible to do dynamically, to, depending on the distance from the camera to your objects, dynamically change the resolution of the map size to account for that loss in resolution? Or
yeah, sure, you can totally change that on the fly. Yeah.
Mm-hmm. So how much you showed the performance measurements for the different map sizes. So like how much, like percentage-wise, roughly, is the creation of the map size actually the influencing factor on that frame rate? Because you provided the total FPS, not just the creation of the map size.
On the paper, you have all the details on what's the cost of each stage, and what is the more expensive to compute here is the anticipation, because of the integral we have.
Okay, so in that case, one of the other questions that we got kind of plays into that as well. So right now you're computing the anticipation map every frame. Like depending on the velocity of the things that you have in the scene, I guess it would be possible to reuse that anticipation map for a couple of frames at least, or particularly if you're in a game and you have, like, say, the second object is something that you control via a spline, you have much more information about that object's position into the future. So that could give you some optimization as well, right?
Indeed, I don't speak about all the optimization we have done in this presentation, but there is two major optimization we've done. The first one is taking this as a hypothesis, and we instead of recomputing each all the instead of doing the projection each frame for each sample, we are taking only one sample, and we consider that it's valid for a time window. So for each time window, this information is valid. We recompute it.
Okay, so you basically know. Yeah, that makes a lot of sense. That's cool. And just quickly check if there are any questions coming in. That does not seem to be the case. So then I would like to thank you once more for really interesting talk and paper as well. And we'll move over to the next presentation that is given by Hang-Yung Song about efficient minimum distance computation for solids of revolution.
Thank you. Hi, my name is Sang-Hyun Son, a second-year graduate student at Seoul National University. In this talk, I would like to present an efficient minimum distance computation algorithm for solids of revolution. This is a joint work with 3 other authors. Let me first show you a few videos that demonstrate the performance of our algorithm. This kind of simulation requires collision detection between concave part of the rings, and we can handle these cases more efficiently than conventional algorithms. Our algorithm performs much better in these circumstances. Since distance computation between rings is very efficient and precise, we can run this kind of massive physical simulation in real time with only single core and single thread. This is the outline of my talk. After related work, I will briefly review the solid of revolution and then an efficient algorithm to compute the minimum distance between toroidal patches. After that, I will summarize the overall algorithm with some details and then present the experimental results and finally conclude the paper. There have been many previous results on computing minimum distance for convex objects. GJK and Lin-Kenny algorithm are the most efficient algorithms. For non-convex objects, conventional techniques are based on bounding volume hierarchy of convex bounding volumes, such as OBB and sphere-swept volumes. In the case of planar curves, non-convex bounding volumes have been used quite extensively in many algorithms. For surfaces, there are only very few previous results using non-convex bounding volumes. In Liu's previous work, toroidal patch had been used for a precise approximation of freeform surfaces. In this work, we suggest the toroidal patch as a non-convex bounding volume. Now, let me briefly review the solid of revolution. When a planar profile curve is given in the YZ plane, we can rotate it around the z-axis and generate a solid of revolution. The pictures show the POM model we used in this paper. For a precise approximation of the solids of revolution, we first approximate the profile curves using a sequence of biarcs. Here, let me introduce some properties of biarc approximation. In the example shown on the right, you can see 2 circular arcs approximate the original curve. The 2 circular arcs, or biarcs, have the same tangent directions as the original curve at the endpoints. Thus, they preserve the G1 continuity of the original curve. Also, they approximate the original curve with cubic convergence. Therefore, if the curve is subdivided at the mid-parameter, the approximation error is reduced by 8 times. These useful properties of bi-arc approximation makes our algorithm very efficient. To approximate a profile curve using a sequence of bi-arcs for a given precision, we can repeat the curve subdivision and bi-arc approximation recursively until the desired precision is achieved. The images on the right show the result of bi-arc approximation. The blue and red curves are all circular arcs with G1 continuity and approximate the original curves within a given precision. We can use bi-arcs to approximate the solids of revolution. When we rotate them around the z-axis, we get toroidal patches. These patches approximate the solids of revolution with the same precision as the bi-arcs. Also, they are G1 continuous as well. This property plays an important role in computing the minimum distance. I will get back to this issue when we discuss the minimum distance computation for toroidal patches. Now, let's talk about toroidal patches. A torus can be parameterized as follows. By restricting the v parameter, we can get the toroidal patches generated by rotating our bi-arcs. Therefore, we need an efficient way of computing the distance between these kinds of toroidal patches. However, when it comes to complex-shaped toroidal patches as shown in the slide, the minimum distance between them is not quite obvious. In the picture, the pink line segment shows the minimum distance between the toroidal patches. Clearly, it's hard to find. If we want to find true minimum distance between these patches, we have to consider every possible case. We have to find minimum distance between inner part of the patches, and also have to find minimum distance between boundary circles. However, as I mentioned earlier, the toroidal patches we use are connected G1 continuously. Therefore, we do not have to consider these boundary cases anymore. This property narrows down our job to only finding minimum distance between inner part of the patches. And to do that, we have to find binomial lines between inner part of the patches. Here, we define binomial line as a line that goes through two geometric entities orthogonally. We can find such binomial lines by solving multiple constraint equations together, but we found much easier way. That is, we found that binomial lines between toroidal patches are also binomial lines that connect two major circles of the patches. Please look at this image. The two major circles of the toroidal patches are rendered in blue. This major circle corresponds to a smaller patch here, and this major circle corresponds to a bigger patch here. You can see the extended version of the pink line before also goes through these two major circles orthogonally. Therefore, we can say that 2 points on toroidal patches that form binomial lines and maybe minimum distance must be on the binomial lines between the major circles. With this observation, instead of finding binomial lines between two multivariate surfaces, we can just find binomial lines between two univariate circles in space. Clearly, it is much more efficient. Therefore, we need an algorithm to find binomial lines between two circles in space. Here, it is known that at most 8 binomial lines can occur. We can set up the degree 8 polynomial by using coplanarity condition depicted in this picture. Please refer to the appendix of our paper to see the proof. Now, we can just solve the polynomial and the roots of it lead us to binomial lines between two toroidal patches. Additionally, We used Gauss maps of the toroidal patches to speed up our algorithm. Since Gauss map shows possible normal vectors of a toroidal patch, binomial lines between two toroidal patches can only occur in the intersecting subsets of Gauss maps. In the slide, those intersecting subsets are rendered in yellow. Therefore, instead of searching for binomial lines in the entire domain, we can find them only in the yellow regions. This shows how our binomial finding algorithm works between two rotating toroidal patches. The green shows the intersection of two Gauss maps. The red line segments show the binomial lines. Now, let me introduce the overall algorithm. First, to build bounding volume hierarchy for our solids of revolution, we have to first approximate the profile curves using a sequence of biarcs and lines. By rotating them, we can generate toroidal patches, conical patches, and cylindrical patches. We use cones and cylinders to accelerate our algorithm. Even though they do not approximate models as precise as toroidal patches, it is easier to compute distance between them. Also, in our implementation, since all of the models were Z-monotonic, we could make them truncated solid cones and cylinders. It further accelerated our algorithm very much. Next, I'd like to talk about distance computation algorithm very briefly. We basically follow the computation scheme from this work. The majority of distance computation algorithms follow this scheme, but our algorithm has some differences in details as we use toroidal patches. To find minimum distance between two hierarchies, we have to maintain a priority queue. We insert a pair of nodes with its computed distance. We initialize the queue with a pair of root nodes from the hierarchies, and in each step, we pop a pair of nodes with the highest priority, which has the shortest distance. While the queue is not empty, we pop a pair of nodes. If both of the nodes were leaf nodes, we can compute minimum distance between toroidal patches. In the image below, D indicates the minimum distance between toroidal patches. Then, we can use approximation error to get upper bound of the local minimum distance. Let this point was showing the previous global upper bound of minimum distance. Then, since the newly found upper bound is smaller than the previous one, we can update the global upper bound with the new value. In the other case, at least one node is not leaf node. Then we compute minimum distance between conical or cylindrical patches. Then, as we did in the previous slide, we can use approximation error to find lower bound of the local minimum distance. At that point, if the current global upper bound was larger than the local lower bound, we must investigate child nodes because local upper bound in the end could be smaller than global upper bound. Therefore, we push child nodes into the queue. On the contrary, if the current global upper bound was smaller than the local lower bound, there is no chance to have smaller local upper bound than the current global upper bound in the end. Therefore, we delete the pair of nodes from further consideration. Finally, if the queue is empty, we can just return the global upper bound as the minimum distance. Please see our paper for more details of the algorithm. Now, let me show efficiency of our algorithm by comparing it with other algorithms. Using these 5 different static models, we have compared minimum distance computation time in various precisions. In this video, you can see that our algorithm runs much faster than the other algorithm. Let me give some more details of the comparison results. This graph shows the computing times. Our algorithm, shown in red, runs 10 to 100 times faster than the conventional algorithm, shown in blue. As the precision goes up, our algorithm works even better. This is because toroidal patches approximate the models much more precisely than other bounding volumes. These tables show data size and the number of nodes required for the bounding volume hierarchies. You can see that our algorithm is much more compact than the conventional algorithm. In our approach, instead of building the data structures for the entire surfaces, we consider only the profile curves. This means that we need to construct special data structures for 2D planar curves, which are often more than 1,000 times smaller than the conventional ones for surfaces. This helps us to apply our algorithm to deformable objects. Therefore, we also tested our algorithm with dynamically deforming objects as shown in the slide. We could build bounding volume hierarchy and compute minimum distance simultaneously in real time. In this video, we can see that the models change from one another and compute distance at the same time. The left graph shows minimum distance computation time for a deformable model. The right graph shows bounding volume hierarchy construction time for all the models. Clearly, the build time is much longer than the distance computation time. However, since they only need a few milliseconds, we can compute minimum distance between deformable objects in real time. Finally, I would like to show you physical simulation once more. As I stated at the beginning of the talk, we can run this kind of massive physical simulation in real time. This is because our distance computation algorithm for toroidal patches is very fast and precise. Let me conclude my talk with three main contributions of this work. First, toroidal patches can approximate solids of revolution much more precisely than conventional convex bounding volumes, such as bounding boxes. Second, we can find binomial lines between toroidal patches by solving degree 8 polynomial. Finally, we can reduce the size of data structure since we build hierarchy for planar curves, not surfaces. Therefore, we can compute the distance between deformable objects in real time. This is the end of my talk. Thank you for your attention.
All right, another very interesting talk, and I'll start with the questions while we're waiting for more questions to come in via the YouTube and the Discord. So I guess the first question that I would have is for in the paper you have 5 experimental items that you're considering. Just to get a rough estimate, like into how many different patches have you subdivided those profile curves in order to do the computation?
It heavily depends on the precision of the algorithm. We tested each model with 10. We tested the algorithm with many precisions, and
the patch size depends on the such algorithms. You can see the paper to learn about those sizes.
All right. Another question that I would have is in the talk you mentioned that you were using biarcs for the approximation of the patches. Why did you use biarcs and not other higher order splines or other kinds of splines like Catmull, Rom, Bézier, as long as they have some kind of G1 continuity?
Yeah, I agree with the idea, but even though higher order splines can approximate the given models much more precisely, we have to consider the computation cost to find minimum distance between them. Since those higher order splines have much higher computation cost when they are rotated around the axis than the simple biarc patches, in those cases we have to solve much higher order equations than these toroidal patches. We use toroidal patches because we can just solve the univariate equation, and it is very easy and computation cost efficient.
Yeah, that makes a lot of sense. Thank you. We've got another question from YouTube from Yunku Kang. Does the BVH need to be rebuilt under model deformation, or can we use it?
Yeah, under the situation, we have to build the BVH each time for the each deforming frame. Yeah. However, because the computation time is really short, we can achieve such deformation situation very efficiently.
Exactly. It was like below a millisecond, right, for recomputing that?
Yeah. Mostly under millisecond, and yeah, that's right. Yeah.
So then I guess my last question would be like right now you're considering rotationally symmetric objects with the profile course, obviously. Would it be possible to generalize that to other kind of geometric entities, like specifically concave objects?
Yeah, as you could see in our presentation, we can handle those cases where there are only tori or solids of revolution. We can handle those cases in very fast and accurate manner. However, when it comes to general geometric objects, it is not so easy. This is because conventional bounding volumes such as rectangular swept spheres show very efficient distance computation time than torus. It is just the same as the higher order splines that you mentioned before. Even though torus can still approximate general objects much more precisely than those convex objects, trade-off between precision and computation time exists. And now I'm working on the issue to reduce the trade-off as much as possible for applying to those general objects.
Yeah, cool. So I see we've got one more question coming in from YouTube from Joachim Thorin. Usage of biarcs to approximate the curves can introduce an error to the minimum distance. Have you analyzed this error? How large can it get?
Yeah, but the error is estimated by the approximation error between the biarc and the original curve. As I mentioned before, we used the approximation error under many circumstances, and yeah, the approximation error just becomes the minimum distance computation error in the end.
Yeah, and you can just crank up the resolution of the splitting in order to reduce the error, yes.
Yeah.
Great. Okay, let me just quickly check if there are any other questions. That does not seem to be the case, so let's thank you once more for a very interesting talk. And with that, we move over to the final talk of the session, which is given by Eric Dahlin about segment tracing using local Lipschitz bounds. So let's go with that.
Hi everyone, and welcome to this session. I am going to present segment tracing, which is a new algorithm for computing the intersection between a ray and a procedurally defined implicit surface. First, recall that an implicit surface is a volumetric object defined by a field function f. The surface S is indirectly defined as the set of points in space that satisfy the condition f of p equals 0. Implicit surfaces have proved to be a powerful model for creating and animating shapes of arbitrary topology. They are used in a variety of applications, such as fluid animation, organic shape modeling, and shape reconstruction. One crucial aspect of implicit surfaces is that they define complex objects possibly with many details, in a very compact function representation. Procedurally defined implicit surfaces have gained popularity by the beautiful procedural models developed by Inigo Quilias, such as this beautiful ladybug surrounded by grass beads and mushrooms. While implicit surfaces are powerful for modeling elaborate shapes, visualization remains a computationally intensive process. Polygonization techniques convert implicit surfaces into triangle meshes, which are in general memory consuming compared to the otherwise compact implicit representation. Direct ray tracing is another option, but it's even more computationally demanding. Parallel implementations using graphics hardware partially alleviate the problem. Nevertheless, ray tracing needs many field function queries. In this presentation, we address the acceleration of ray tracing. Given an implicit surface characterized by its scalar field f, and a ray defined by its parametric equation delta, the challenge consists in finding the roots of the function f of t while using the minimum number of field functions evaluation. Several techniques have been proposed for computing the ray implicit surface intersection. Here we briefly review different approaches. Analytic techniques aim at computing the piecewise closed-form expression of the field function along the ray. When f of t is a polynomial equation, solutions, and thus intersections, can be solved analytically for low-degree polynomials, or by using Bézier clipping. Another solution consists in approximating f of t by a low-degree polynomial to speed up processing. Yet this is performed at the expense of less accurate intersections. Interval analysis redefines the function f over intervals and relies on interval arithmetic to evaluate f. This approach performs well for scalar fields with simple closed forms expressions, such as polynomials. This approach does not lend itself to procedural implicit surfaces, however. Starting from the ray origin, ray marching consists of stepping towards the surface with fixed steps. This approach does not require any knowledge about the field function f, but is computationally exhausting and not robust. Lipschitz functions provide an interesting framework for ray tracing implicit surfaces. Sphere tracing, in particular, requires the knowledge of a global Lipschitz bound of the field function. Contrary to ray marching, the algorithm uses adaptive steps and provides an exclusion criterion to avoid stepping through the surface by accident. One limitation of this method is that it relies on a global Lipschitz bound only, which reduces the overall performance. This is a very drawback, and this is what we address in our work. The motivation of this work is to provide a memory inexpensive algorithm for evaluating local Lipschitz bounds on the fly. Our approach takes advantage of the hierarchical and procedural definition of the implicit surface. We evaluate the Lipschitz bound locally at every step of the marching process over a candidate step X segment. Our method yields tighter Lipschitz bounds, which in turn allows for longer steps and significantly reduces the number of iterations. So let's have a look at the algorithm. Recall that the function f is Lipschitz if and only if there exists a constant lambda such that f of p minus s of f of q is lower than the distance between p and q times lambda. The interesting property is the exclusion criterion. The sphere centered at p and with radius f of p over lambda does not intersect the surface. Sphere tracing takes advantage of this property. At every step, it is safe to step forward by an adaptative increment f of p over lambda. Unfortunately, while stepping adapts to the value of f, the Lipschitz constant is global. Therefore, our goal is to compute the local Lipschitz bounds at every step, which should be smaller than lambda. Consequently, the stepping distance should increase, which will eventually result into fewer field function evaluations and a faster algorithm. Here is a short animation of sphere tracing that shows how steps adapt according to the scalar field values. In contrast, segment tracing performs as follows. We first initialize a candidate stepping distance epsilon. At every iteration, we analyze the field function f over a candidate segment and compute the corresponding local Lipschitz bound. We then compute the stepping distance as the minimum between the candidate stepping distance and the Lipschitz stepping distance f over lambda. Taking the minimum guarantees not to move further than the candidate distance for which we analyze the field function. At the end of every iteration, we update the length of the candidate segment, and we will comment on this coefficient later. In this example, we illustrate the benefit of segment tracing over sphere tracing. When the ray gets close to the surface, the local Lipschitz bound remains small and allows for longer steps. The factor kappa defines the next candidate marching step according to the previous stepping distance. Small values tend to preserve the locality of the computation of the Lipschitz bound during the algorithm, whereas larger values increase the candidate marching step when marching away from the surface, thus resulting in fewer steps. In other words, small values make the algorithm stall when the ray comes close to the surface, and large values generate long candidate segments, which in turn produce larger Lipschitz bounds, which decrease effective stepping distance. In practice, setting kappa to 2 proves to be a good choice in most cases. Now the challenge consists in evaluating the local Lipschitz bound of the field function. Here we consider an implicit model defined as a hierarchical construction tree. The tree combines skeletal primitives with blending, Boolean, warping, and affine transformations. The field function f is evaluated by recursively traversing the tree. The leaves contain skeletal primitives, and their field function is defined as the combination of a fourth kernel function applied to the Euclidean distance to their geometric skeleton. Here, a sphere primitive was used to create the roof, and segments were used to create the pillars. The internal nodes of the tree contain operators such as intersection, blending, or warping. Here we used an intersection with a box to cut the sphere of the roof in half, and warping could be used to carve decorations in the pillars. The challenge consists in defining the Lipschitz bounds for all types of primitives and operators. Before reviewing different types of nodes, recall that computing lambda over a segment may be difficult in some cases. We rely on the following strategy. Whenever possible, compute lambda of E as accurately as possible. This can be effectively achieved for primitives built from convex skeletons, blending, and Boolean operators. Complex cases include warping operators that deform the segment into a curve, and non-convex skeletal primitives. In those difficult cases, we resort to coarser bounds, which are simpler to compute. In general, we evaluate lambda over a sphere embedding the segment E, or even compute lambda over the entire ray supporting the segment E. While those bounds may be less accurate, they are easier to compute and are still a better approximation than a global Lipschitz bound. For primitives, we analyze the derivative of the field function along the ray and bound this derivative. After developing the closed form expression, two terms arise. The first one involves the derivative of the fourth function, which is easy to bound over the segment using interval analysis. The second one involves the scalar product between the gradient of the Euclidean distance to the skeleton and the derivative of the ray, which is in fact the unit direction. For some simple geometric primitives, such as points, segments, or disks, we can compute an accurate bound this way. This example shows that computing a tight bound is very effective for the parts of the ray that tend to be orthogonal to the gradient of the field function. During the adaptive marching process, those cases occur in particular whenever the ray gets close to the primitives, especially at grazing angles. Let's have a look at operators, and let's start with the easy ones. Formation of a segment on several objects combining different large models. First, results show that our method significantly reduces the number of field function calls, sometimes by up to 2 orders of magnitude. This can be seen on those images showing the number of field function calls. Here we show the gain in terms of field function calls for different local Lipschitz-bound strategies, along a ray, in a sphere, and over the candidate segment itself. Calls Lipschitz-bound over the ray or the sphere also reduce the number of field function calls, but to a lesser extent. Still, as we mentioned earlier, we may need to adapt the local size in terms of lows, the Lipschitz coefficient region, which is simpler to evaluate. This example shows the benefits of computing an accurate local bound for a tapering operator that shapes the stem of the table. With a global bound, many iterations are necessary to check the ray surface intersection in the tapering region. In contrast, computing a local bound along the stepping segments drastically reduces the number of field function calls. Affine transformation are a special and simple case of warping. The transformation of a segment remains a segment, so the gradient of the child field function is also evaluated over a segment, and the spectral norm is simple to compute. The results are as follows. The Lipschitz coefficient applied to the subtree is 1 for rotations and translation, and the inverse of the scaling coefficients for scaling. We have covered a variety of primitives and operators for which we have algorithms for computing a local Lipschitz bound. Now, let's have a look at the results. We tested our algorithm on several objects, combining different kinds of primitives and operators. Here are a few examples of objects that have been implemented and tested. Some objects, such as a chess king or the amphorer, are made of a few geometric primitives, such as points, curves, or even surfaces of revolution that are combined together with blending and Boolean operators. Those objects were used to test the effectiveness of the local Lipschitz bound for primitives. The temple is an object of moderate size in terms of number of nodes, featuring many Boolean and blending nodes and replication operators. The cluster and molecule models are typical objects consisting of thousands of point primitives blended together and were used to test the performance of our method with large models. First, results show that our method significantly reduces the number of field function calls, sometimes by up to 2 orders of magnitude. This can be seen on those images showing the number of field function calls. Here we show the gain in terms of field function calls for different local Lipschitz bound strategies, along a ray, in a sphere, and over the candidate segment itself. Calls Lipschitz bound over the ray or the sphere also reduce the number of field function calls, but to a lesser extent. Still, as we mentioned earlier, we may need to adapt the local Lipschitz evaluation on the fly when traversing the tree, depending on the type of node. Segment tracing also speeds up the algorithm by 1 to 2 orders of magnitude. Reducing the number of field function queries does not necessarily improve computation time by the same amount. The accurate Lipschitz bound computation comes at the price of extra queries. The ray algorithm requires 1 bound computation for the entire ray and multiple field function evaluation, whereas the sphere and segment algorithm require multiple queries to evaluate both f and lambda at every step. Careful implementation is needed to avoid redundant evaluation during the traversal of the tree. In particular, common terms frequently used by primitives and operators, such as the segment length and its unit direction, should be stored in the segment data structure. Finally, here's a comparison of our method with an octree accelerating data structure storing local Lipschitz bounds. This is a typical storage computation trade-off. Results show that for depth below 7, segment tracing performs faster than octrees. Finally, remember that segment tracing performs all computations on the fly and thus preserves the compact aspect of procedural implicit models. We are about to finish. Let's review and conclude. We have presented a method for computing the local Lipschitz bound that allows us to better adapt the marching distance and speed up the ray implicit surface intersection computation by 1 to 2 orders of magnitude. Accelerations come at the price of extra queries to compute the local Lipschitz bounds using different strategies. A direct extension of our work is to implement and optimize methods for other categories of primitives and operators. Another promising avenue of future work, which we are currently investigating, is to analyze and compute accurate Lipschitz bounds for multi-frequency noise functions, which are often used in procedural modeling and solid texturing. Thanks for watching.
Okay, another very interesting talk. So let's, while we're waiting for the questions to come in, I will start. You already alluded to that in the end with your future work. So could you expand a bit on how you would expand the Lipschitz bounds to computations of other kinds of primitives or other kinds of elements like noisy functions and other kinds of those kind of things?
Well, in essence, the algorithm requires the implementation of the constant, of the Lipschitz constant for all kinds of primitives. And Perlin noise or Worley noise are operators or primitives depending on the implementation, and they would require very specific code. Quite difficult because the problem is that you have to compute the Lipschitz bound for any segment. And when you compute sum of noises, a solution would be to compute the Lipschitz computation for 1 octave and then scale everything for different levels. And then you can have results that would probably increase and speed up the algorithm. This is a very interesting question because sums of noises are often used for modeling rough surfaces or terrains or different kinds of objects, eroded surfaces, for instance. They are widely used in Shadertoid as well for producing nice objects. So, well, yes, there's a lot of work that would be interesting to launch in that direction.
Would there be any use in? I know that your work is focused on implicit surfaces, but would there be any use for? Let's say I make a new implicit surface and I already can compute ahead of time some Lipschitz bounds and give you that as some kind of other data representation that you could use as a first approximation of it, or doesn't make any sense at all?
I'm not sure I understand your question quite well.
So right now you're computing the Lipschitz bounds for each of the ray marches, right? In order to optimize the ray stepping. Yes. And I guess you're saying with the noise function, the problem is that is not a very easy computation to do. Yeah. So if I already know that I'm going to use a noise operator, and I ahead of time compute an upper bound for the Lipschitz constant.
Okay. In essence, the problem is that in this implementation, this work, we tried to compute the Lipschitz constant on the fly without any pre-processing. So, of course, a solution would be to evaluate the noise function in advance and maybe store some local Lipschitz constants, which could take some time. But again, this is a typical trade-off between performance and storage. I think that it's possible to evaluate the constants on the fly, because in the case of Perlin noise, you can compute the derivatives analytically, and then this means that you could also compute the upper bound of the derivatives on a local basis. In other cases, of course, you might need to resort to some pre-computation and storing, but this is the kind of things we wanted to avoid in this very specific work.
Sure. But it might be useful to combine the two of them to get the best of both of the worlds.
Yes, always combining the two techniques will be going into a hybrid direction would be worth investigating.
So we got one question from the Discord from Gabor Valasek. How did you define the primitives in the CSG trees? For example, or that is, were they signed distance lower bounds, exact functions, or general implicit functions?
In fact, in those cases, the implicit primitives are defined as a decaying function of the distance to a skeleton. So let's say if you have a skeleton that is a segment, you first compute the distance between a point and a segment, and then you apply a fourth distance function, which means that the intensity will be maximum on the segment and slowly decreasing as you move away from that segment. But the algorithm is general. I mean, we tested our model not only on the blob tree, which uses skeletal primitives, but you can also process distance field. I mean, analytic distance fields or SDFs or other kind of models. The key point is to be able to derive a local Lipschitz bound for every kind of primitive. So as long as you can do this, our method could be adapted to different models.
Mm-hmm. Let me see if they're... See that Gabor is typing. No, he just says thank you, which I wholeheartedly agree. So if there are no other questions than that, then I think we can finish with the session. And I just want to thank all of the presenters once more for very, very interesting talks. And with that, we'll close this and we'll meet each other after lunch or breakfast or dinner, wherever you are. Thank you all.